Live streaming is on.
Okay, and we should be live. Welcome everybody to another tutorial as part of Transform 2022. This one is going to be about PyGIMLi, which is an open source library for geophysical modeling and inversion, written in Python. So this is part of Transform 2022, which has a bunch of openly accessible tutorials and similar things related to geoscience, particular digital geoscience. We'd like to thank curvenote.com for their support of Transform. If you're curious about the schedule or what else has happened and what is going to still be happening, because we're about halfway through, have a look in the description. The schedule is at softwareunderground.org/transform. If you'd like to get involved with some of the live tutorials and ask questions while they're happening, have a look at softwareunderground.org/Slack. And for this particular channel, you want to have a look for T22-MON-ML-models. Just a reminder, you can pause and rewind this video even if you are catching it live, but otherwise, we'll see you. I'm going to hand over to Thomas Günther, who will be taking us through a bunch of stuff for PyGIMLi. So take it away, Thomas.
Yeah, thanks, Martin. Thanks for the introduction. Thanks to all the sponsors of this event, for all the organizers from MAT for inviting us to this really great event. We've been starting to present PyGIMLi already last year, and it was a great success. Since then, the video was looked, I guess, like 5,000 times, and that's why we thought it's a good idea to have a follow-up of our geophysical inversion and modeling library PyGIMLi. Actually, the title isn't very different, but the focus will be a little bit different. So I'm sharing my screen, so you will see the README file of the repository that you hopefully have in front of you. Otherwise, you can have a look at the main page of a tutorial. I'm gonna starting with introducing my co-authors. I'm Thomas, and then there's Carsten. Carsten Rücker is the main developer of PyGIMLi. He's really the one that coded all the nasty, dirty C++ stuff and everything in the back, and he will be also in the back of a Slack channel, which is also linked on our README file. It's T22 PyGIMLi on the Software Underground Slack channel, and there's also Florian Wagner, who cannot be here today, but who did a lot in promoting and bringing forward PyGIMLi. We're going to give a talk about geophysical modeling with PyGIMLi. I'm going to start with a quick review of what we did last year. Maybe you didn't see the talk. Maybe if you haven't seen the talk already, it might be a good start to start with that one. It will also be linked. When I'm giving you a view of last year's presentation, I just want to show some slides on what we did last year. So we presented some ability of PyGIMLi regarding the mesh generation. So we worked with 2D and 3D meshes. We've created a mesh, having some layers in the background and having some anomaly in it, and showed how easy it is to control this mesh in such a Jupyter notebook. The second notebook was to use this created mesh and to simulate it. I find an element analysis of a heat equation, a simple Laplacian equation, and we solved this and we presented the heat distribution and heat transfer lines and everything. This is number 2. Then next we designed a crosswell travel time experiment. So we set up a scheme of geophones and transmitters, and then we used the same anomaly also for making tomography, a seismic tomography, which we in the 4th notebook inverted. So we took some synthetic data and we did an inversion of those synthetic data and showed ray paths and everything. So this is pretty much how you readily use how you can readily use PyGIMLi, which was also demonstrated for ERT data. For those of you not familiar with ERT, you might have a hard time this time because it will mainly be on ERT this tutorial. But everything we do and demonstrate is can also be transferred to any other geophysical imaging technology. So the electrical resistivity tomography was used to read in some feed data and make some inversion and control the inversion just a little bit. So these are pretty much ready-made tools that you can just copy and paste from the web page. And in last notebook, we started doing something more complicated. We used the very nice open source toolbox MPyMod as a forward solver and put this external library into our inversion machine and did some EM 1D sounding of some synthetic model. That's what we did last year. But our idea now is to present PyGIMLi more as the toolbox that can be that can be used to solve specific problems rather than the ready tools for solving already existing problems like inverting ERT field data. That's why we want to go a little more into details, a little more into the under the hood of PyGIMLi. For any documentation, I'd like to refer to the PyGIMLi web page. If you go to pygimli.org, you find a lot of stuff on the web page. You can see a lot of nice papers that we, but also other people completely independent of us, made with PyGIMLi, and this really speeded up. So in these 3 years of publication, we had already 160 references to the main paper and a lot of PyGIMLi related papers. And you can have a complete list of those papers that are really actively using PyGIMLi here. But there's also a lot of documentation. You can have a look at the PyGIMLi API. You can look at every function. You can look up how different functions are looking like, and API documentation. You can have a look at installation routines. You can watch a lot of tutorials, which are really teaching basics, and this is pretty much what we're doing right now, which is what we will be doing today. Actually, the tutorials that we're going to present will become parts of this tutorial collection, and then there's also examples which are pretty much what we did last time, like crossover travel and tomography, or illustrating brake paths, refraction modeling, resistivity, IP, gravity, magnetics, Darcy flow. So you can see PyGIMLi is actually not only being used for resistivity tomography, there's a lot more. Okay, going back, today we want to go in the very first part a little into the details of some very important PyGIMLi classes, which are the DataContainer, the mesh class, several matrix types, model and data transformation, and introduce some frameworks. We will discuss the geostatistical regularization, which is not totally new, but we haven't touched this last year's tutorial, and discuss it against classical smoothness types. We will demonstrate you how to treat individual subsurface regions differently, so that you can really have hands on your inversion. So inversion won't stay a black box for you, but it will be something that you can actively use. And this is also nicely illustrated by the fourth notebook, which is dealing with the incorporation of prior knowledge into an ERT inversion, which can, of course, also be any other type of inversion. And we quickly discuss different kinds of joint and coupled inversions. We probably will have little time to talk a bit about induced polarization modeling and spectrally constrained inversion, and it will at least give some outlook on what we're currently doing, and also shed light on some other packages that might be of interest for you from the PyGIMLi ecosystem, which are named here. So before the tutorial started, this was already written on the GitHub page, which is also linked in transform. It's under the Rücker and GIMLi or transform 22. You will see all the notebooks here. Those are the ready-made notebooks that can be followed just by clicking through it. I will step by step start from almost empty notebooks because this makes it much easier for you to follow. We also provided some data that we are going to use, and there's also some environment YAML been given, which can be really easily used to create your Python environment using the Conda environment. So what you have to do, that's the quick setup, is to get hands on your data, for instance by git clone or by downloading the zip file from the project page, then change into this directory, create an environment, activate this environment, and then start Python and test PyGIMLi. We will be using JupyterLab, but of course you can also use any other IDE like VS Code or Spider or Jupyter Notebooks. There's not much different. You can see I'm already in the JupyterLab environment. So I've already started this JupyterLab command, which will open right at the position where we are. You can see on the left-hand side, we have a little more in the file browser. You see the data folder that contains some of the data that we're gonna use in this tutorial. And then I have actually two versions of this tutorial because I have blank versions with only the necessary steps. So whenever you have problems following those installation routines, you can go to the Slack channel and talk to Carsten, paste your errors or whatsoever. But it should be very easy on both Windows, Linux, and Mac. You will need the latest PyGIMLi version. For those of you with an active PyGIMLi installation, you will need the newest version 1.2.5. So download the install the tutorial, and then start Tutorial Lab. And that's what we're going to do today. And I will start with a very quick introduction. So we start with first of a serious tutorial, as we count from zero in Python. In this tutorial, it will not be so interesting as the other ones, but we will dive a little bit more into the main classes, mesh, data container, matrix types, and demonstrate different kind of constraints. That will be the next tutorial, fourth tutorial, regional constraints, and then prior knowledge. In this notebook and all other notebooks, I have already put in some imports at the top so that I don't have to repeat them. Again, what we're going to use is, of course, standard libraries such as NumPy. We're going to have to import PyGIMLi, but we also use matplotlib as plotting library throughout, so we will not do any 3D visualization this time. And we're going to use the Seaborn notebook style, and this is just for making this notebook a little bit nicer. The main important thing, we're going to use pyplot from matplotlib as plotting library. Then we're going to import NumPy, and we're going to import PyGIMLi, and as soon as we imported PyGIMLi, we should print the PyGIMLi versions such as it is also possible for NumPy. And probably in some cases there might be some issues also with pyplot version, just to make sure that we have correct versions. It's not strictly necessary, but in some matplotlib versions there might be some problems, and if this occurs, we can help you out. So testing the matplotlib version is 3.5. There had been some recent issues with 3.5. NumPy is 1.19, but should also work with NumPy 120, 121, and also other matplotlib versions. If not, if there are any problems, this could be the reasons for this. Okay, let's start with the data container. Assume with a very simple idea, just storing data. So we assume we want to store vertical electrical sounding data, and we create an AB, and we have an if you have a spreading of our electrodes array, and you're going to start this into by using NumPy log space. And we start from 1 meter to 1,000 meter. So we're going to specify the exponent of this log space, and we've got this. We have a logarithmically equidistant spacing, and we're going to associate to the variable AB over 2. And actually, what we want to do, and we want to get this into a data container. So what we going to start is we use PyGIMLi data container. So whenever you type PyGIMLi, you will see a lot of things, probably too much, but you can just tap complete. And we will see there are two instances. There's a normal data container and a data container ERT. The ERT is a specialized data container for electrical resistivity tomography, but right now we're going to start with an empty data container, and we're going to call this VES, like a vertical electrical sounding, and then we just print it, and we see what the data container with no sensors and no data. Okay, that's probably very simple. The data container pretty much behaves like a big player or like a NumPy named array, but it has some advantages that are important for geophysics. That's why we created the data container back then. So what I'm doing is I'm using it like a dictionary in creating a new data field called AB2 and getting the values of AB2 into it. And of course, also AB2 times 2, it doesn't matter. The names is just see it. And once you see it, you have an AB2 range of 19. Then you see you have 19 data, which is really nice. And you have one non-zero entries field called AB over 2. Okay. In the next step, we're gonna put something else in. Like for vertical electrical sounding, you usually have a potential electrode spacing in contrast to the current electrode spacing. And well, I just want to put in some other area, and then I'm having an error because it's saying it's the wrong data set. But yes, of course, it's a data list and matrix. So actually, I cannot use different data sets. So if I'm using the correct number, there won't be any error. In this case, I will use an error of the same size as AB over 2. That's why I'm using ones like AB over 2 from the NumPy. And I'm going to print it, and now I see I have two properties in my data container. So say we want to do some vertical electrical sounding. What I'm doing is I'm creating a manager. That's what we already did last time when doing ERT and travel time inversion. So I'm going to the correct submodule. So you can enter the submodules in the import routine, but you can also access them step by step. And if I'm going into the ERT submodule, we'll see a lot of stuff which is in the ERT. There's also a VES manager. So I'm going to call that to manager, which is empty. Then I'm going to model a certain model, and this is a layered model of 3-layer cases. So I have two thickness values, 10 and 10 meters, and then I have 100 ohm meter, 10 ohm meter, and 1000 ohm meters. I have a 3-layer case. And what I'm doing is I'm using this this manager to simulate this model with a given AB over 2 value and with a given Mn over 2 values. Then as a result, we have some numerical values, and as you can see, they start with 100 ohm meters, then they go down towards the 10 ohm meter, and then they go up again, which is somehow nice, but you have a none value. Actually, a nice idea, which is very simple to say, because our mn over 2 values already start with 1 meter, and our AB over 2 values start at the same position. So we have current and potential line at the same position. That's why I'm going back and I'm using a smaller electrode spacing. And now you see you have you don't have any none values, and the result we also put into our data structure, and we call it apparent resistivity. It's just a name, so there are no predefined structure. You can call it whatever you want. And then you see you have free data in these structures. So how's this going to look like? I'm going to use pld.subplots. And this is having a figure in axis in matplotlib, and then I'm going to use this to make a log-log plot of all the apparent resistivity on the x-axis, and I'm going to use the AB over 2 on the y-axis, and I'm going to plot it with axis and so. And then you have the curve. I'm going to add some magic to it, which is turning the limits up and down, adding a grid to the axis, and having some labels for the apparent resistivity on the x-axis and the AB over 2 on the y-axis. So what we have is our measuring curve starting with a first layer resistivity, then going down, not quite to the second layer resistivity, and then going up and also not reaching the upper resistivity. Okay, this is how it looks like. What we usually want to do is for any other purposes is to save this stuff. And then the data container has a lot of options. So you can do a lot of, you can add points, you can check the validity of the data. We will do this later. We will create sensors. You can look into the data. And there's also a save function. Look into the docstring. It's coming from C++. It's not looking very nice, but we're going to just call it these.data. And we could look into the data. We can just quickly, and we have the content of this file typed down. So the first part of this file is holding the sensors. In this case, we don't have any sensors, any transmitters, receivers whatsoever. We just have 19 data, and they are organized in columns. And we could also say, well, we just want to have the AB over 2 and the apparent resistivity in columns. And then we see nothing is saved, because the data are, if we take this back, the data have also an additional column which is called valid, and it's unfortunately called it's unfortunately on the outermost column. And this means all of our data are invalid. So what we can do is we can mark all this data valid. There are different marking functions, so you can kind of mask your data, but you don't have to delete them, which is very important. When you process your data, you're keeping your data structure as it is, and at the end, on front of inversion, you can delete your data. So what you can do is mark your data, and then you can say, well, we mark every data with as AB over 2. And then we're going to copy the save structure, the save command. So, we can say every data with an AB over 2 is bigger than 0 is valid. And then we have the 1 at the very common, and then we can also say we only want to store AB over 2 and apparent resistivity in the file. Okay. This is a very simple data container. Of course, we can add whatever other flags, like something like we can have a look at all values below of a certain threshold, like over 100 ohm meter. And we transform this into a standard vector, and then we save also this flag, and then we see that we have marked all values above 100 ohm meters with 1, and our other values with a 0. So we can do a lot of logical operations and so. But very often the data containers become important when you have index data, and that's the next step. So again, we are going to create a new data container. We're going to print it, and it's again an empty data container. Like in this case, we assume we have some sort of transmitter and some sort of receiver. We use the function register sensor index, which means the data called Rx. It's just a definition of just an arbitrary definition. This is a sensor index, so this should not be 1.2. This should be an integer. And the same we do for Tx. And then we have Rx and Tx as fields. They can be accessed like all the other fields, but they are special fields. They are sensor fields. And then okay, something was glitching. Yeah. Okay. Then we create some sensors. So what we can do is we create you create a sensor with a PyGIMLi positions. So what we can do is to add a certain position. And what I'm doing right here is I'm creating a loop. I'm using 10 sensors, and I'm creating a sensor with a spacing of 2 meters. And then I'm have a look at the data. So I still have no data, but I have 10 sensors. And I can print those sensors like PG. And then you see the sensors start at 0, 2, 3, 1, 18. Okay. Now I'm going to add some data to the data container. I'm using the Rx field, and I'm adding some the receiver starts from the very first sensor and goes to the sensor number 12. Don't mind there that we only have 10 sensors. And again, if I want to do the same for the transmitter, and I'm using a different size, I'm going to have an error because the 11 doesn't match the 12. So what I can do is to is to use a NumPy. And use the data.size, which is telling me the number 12. And I'm using the number 2 as a sensor. Of course, we have 12 data and 10 sensors. And we can, of course, save the data file again. Let's call it test.data, and then I'm gonna PyCAD it again. And we see we have our 10 sensors, 2 meter spacing, X, Y, Z, and then we have some Rx values are starting from 1 to 12, and 3 for the receivers. Number 3 for the transmitter, and 1 to 12 for the receiver, which is kind of strange, because we already put in 2 and number 12, and this has some historical reasons, because right now we started with ERT, and we defined the number 0 as an infinite electrode, as a remote electrode, and we started to count real electrodes as number 1. Actually, we started from MATLAB, and this is why it's indeed a bit strange. You can change this behavior by setting a different data type, but for historical reasons, we will stick to it. Okay, so we have some receiver, we have some transmitter, and we're gonna gonna do something else with it. So we can again mark all the data valid, so that we don't fall into any problem. So we can mark all transmitters valid, and then we can also print the validity of the data, and this is valid all the time. So there is something in it. And but of course we know that we still have numbers here that are integer numbers referring into the sensor list, but there are only 10 sensors. So actually there's something wrong. That's what we're going to do with check data validity, and then we're going to print the data again, and then we see, okay, we have 12 data before, but now after checking the data validity, two data have been deleted, and we now print the print it again, the file, and we see that the number 11 and 12 have been removed because they are invalid, because they're referring to a sensor that doesn't exist. Okay, we can do some other computations with it. For instance, you can extract the sensor X is pg.df data, and then we're gonna define the distance between transmitter and receiver. And we use the absolute difference between the SX value of a RX receiver minus the X value of a PX receiver. When you have a distance between transmitter and receiver, we remember that the transmitter is the third index, so that's why we have a 0 distance here, and we have an increasing distance between transmitter and receiver to both sides. Then we can, for instance, say, well, we don't have a receiver where the transmitter is because this is going to destroy our transmitter. That we can just use any logic expression like data Rx is data Tx. And we see it's still there. It's still 10 data, but it's just marked invalid. If we want to remove all the invalid values, then we see the data has only 9 data entries. And again, we can print the distance function. We're going to see that the 0 from the original distance function has been removed because the transmitter and receiver are at the same point. And so we can do a lot of things with these transmitters with those data. So like inserting create a new sensor. And for instance, we can use the sensor list, and we take just taking the last sensor. The data sensors is gonna produce this all the sensors, and we take from this list the last one and create a new sensor. Probably it's enough to type only data here, and we see we don't have any more sensor. Well, because those are unique sensors, and there's already a sensor at the same position. But if we add a small number, then we see we have 11 sensors because this is a new sensor, and but actually this sensor is not used. So what you also can do at a later stage is to remove unused sensors. This sensor is going to be reduced again, and it's doing all the numbering. And if we insert some sensor in the middle, then we can sort it and everything. So there's a lot of functions in the data container that are not so easily accessible in a NumPy named area or pandas data frame. One thing that might be important is to plot such a sensor, to plot such a data container. And there's a little convenience function. So we go into the viewer submodule. Submodule viewer have different functions, but there's an MPA viewer, and there's a function, a lot of show functions and draw functions for plotting all stuff. And that's, for instance, a plotting function for data container as matrix, and this is plotting the data container with a Rx value against the Tx value, and the distance as a function, and then you see the plot. So you can plot all your data container as a cross plot between your stuff. Okay. Next one is the mesh class. Let's speed a little bit up. Mesh. We have already created some meshes by some automatic stuff. Now we're gonna do some by hand mesh generation, just to show you some. We're gonna create a new mesh and call it mesh. Okay, we're going to print the mesh. It doesn't have any node, cells, or boundaries. So a mesh has node, cells, or boundaries. So what we can do is to create a node at a certain position, the 0, 0 position, and we call it N11. And we create a node, and we have one node. Okay. What we're going to do is to copy this again and again. What I'm going to do is to place two nodes next to each other, one at 1.0, 2.0, then we have already 3 nodes. But from 3 nodes, we cannot create any mesh. That's why I'm going to use another line of nodes, which are having different numbers at the same x positions, 1, 2, and 3, but at different y positions of 1. And just by accident, I'm giving one of those nodes a specific marker, equals 1. If we're going to do this, we have 6 nodes, and we can also already access the node markers. So we have a vector of 0, 0, 0, 1, 0. Okay, then I'm going to create 2 more nodes in the middle, between, even above the 2 nodes. So what I'm going to produce is one row of 2 quadrangles, and then I'm going to use 2 triangles. So I'm using the function a quadrangle, which is using nodes, and 1, 1, and 1, 2, and in the second row, 2, 1, 2, 2. Yes, of course, that's not a correct node, but now I have one cell. Okay, I can also give it a marker, like I'm gonna give it a marker of 4, which is just specifying it's a quadrangle for me, and I do the same again with the next node. So 1, 2, 1, 3, 2, 3, 2, 2, and what I can also do at the very end is show this mesh. When I get rid of those semicolons, then you see two cells that are 2 blocks. But what I also want to do is to create 2 triangles. On top of these, so we have 1 quadrangle, 2 quadrangle, and we see there's a strange node markering because I have created this node like 1, 2, 3, 4, and that's why I have some edges in between. That's why I should turn those nodes around so that they are circular, and then I see the two quadrangles and the 3 triangles. What I can do is to show any what I can see is the mesh does not have any boundaries because we didn't put in any boundaries in, but this can be automatically be done. Create infos. And we see we have 11 boundaries, which are the edges between and at the outside. 1, 2, 3, 4, 5. So 11. So that we also have a triangle here and a convex body. Then we see we have 12 boundaries. So I'm gonna do this mesh again. I can try also the markers. So I'm having a look at the marker, and we see the triangles have a marker of 3, and the quadrangles have a marker of 4, like I specified before. If I'm leaving this marker out, and I just wanted to show you, I'm gonna do some magic copying. What I'm doing is I'm plotting, I'm iterating through all the nodes. What I'm doing is to add a text, add the node x value, node point y value, node point And then the text that I'm going to put here is the node ID. And for this, I'm using the color C0. Then we don't see it because we cannot plot. We have to return the axis object to plot into this. So every show function returns two objects, which is an axis object that you can draw in and a color bar. In this case, we don't need a color bar. That's why I'm returning a blank. But I can see that all the nodes are 0, 1, 2, 3, 4, 5, 6, 7. And the same we're going to do with the boundaries and the mesh cells. So we plot at the center of each mesh cell. We plot the number of the ID of a mesh cell, and at the center of a boundary we plot the ID of a mesh boundaries. And then you have the whole mesh plotted here. So you have the 0 mesh cells 0, 1, 2, 3, 4 in the order they were created, and we have the boundaries 0, 1, 2, 3, 4, 5. So we can access all those boundaries, and of course we can also access node markers, cell markers, boundary markers, and boundary markers have something to do for boundary conditions, for finite element computation, and so on. Okay. I'm going to skip the next one. What I'm going to do is I'm going to have some quantity. I'm just using an RPA range of the node count, and I'm just adding a number of 10, and then I'm going to show the mesh and the voltage. Then you have the voltage distribution because it's the lowest here, and then it's from 10 to 17. And similarly, I can also show any other property that I can also put into the mesh. So I can also use the mesh like a dictionary, and I can do something like mesh velocity is in this case we need a cell count. So adding 10, and then we're gonna show the mesh with a mesh velocity as property. Then we have the velocity distribution that we just ordered from 10 to 14. Okay. What we can do at last with meshes is we can save it under a binary format, but we also can save it as a VTK file and have a look at the VTK file then. Oh yes, the call is export VTK. And VTK file looks like this. It's also a very familiar format. So you have 8 points, 5 cells, and there are quadrangles and rectangles with different types. And we also have the velocity function in there. You don't have the voltage because this was just defined outside. Okay. Now we're gonna step to the next important point. We have different matrices, and I just want to go quickly through it, through the matrices. But they are important for also for the constraint, for the regularization. That's why I want to go into details about a little bit into details. So there's a dense matrix called matrix. So we can change. So we can initialize such a matrix with a size. And you see a matrix which is full of zeros, and then you can index any values. It's just like an NumPy matrix. But what you also can do is you can also access whole rows. of a matrix like an A range of 4, then you have an 1, 2, 3, 4 in the second row. So this is a very often used matrix for everything that stands, like a Jacobian matrix of ERT or whatever. This is very often. This also exists as a complex matrix. Then there's an index. Then there's a index-based sparse matrix, which can be created like a sparse mat, which is a sparse matrix. You can also yes, all the classes are starting with a big S, and it's not so easy to see it, but you can see this matrix. It's 2 by 3, but to see any entries, you would have to set some values, and this is done by setval 0, 0. We put a 1, and then we put some other values in. And then you see the sparsity structure. So we have like a first order derivative in the first row. In the 0, 0 button, there's a -1, and in the next one is a +1, which is actually a second, which is actually a first order derivative. If you multiply it by a model vector, to just take the difference between the second and the first model parameter. And in the second row, there's actually something like a second order derivative, where you put a -1, a +2, and a -1 in there. Of course, you can multiply it by any vector, and then you have a result, which is two vectors. So you can multiply it even with a list or numpy vector or PyGIMLi vector. They are compatible. I'm going to quickly go through our matrix. There's a column compass matrix mostly used for finite element equations inside of a FEM kernel. There are diagonal matrices like the identity matrix, which is which doesn't have to store anyone. So if you want to use an identity matrix, you just have to create one. All the matrices are under the submatrix matrix. You can create an identity matrix of 4, and then you can multiply yes, of course the dimensions have to match, and then you can multiply any vector by it, and then you have the same vector as an output. Then there are weighted matrices where you can use this matrix like initialize a standard matrix of 3 by 4 and adding a value of 1 to it, so that we have 1 values in A. And then we have a weighting vector, which is containing some numbers for the weighting, and then this is a mild-left matrix, which becomes important for the constraining for the regularization. And we multiply the weighting vector from the left with a matrix, and then again we can use multiply this with a vector of a length 4, and then we have a value like this. So the weighting takes goes into this matrix B, but we don't have to multiply, but we don't have to create this explicitly. So there's also a weighting from the right-hand side and weighting from both sides, and we're going to use this for Jacobian matrices, transformations, or whatever. There are combinations of matrices like multiplication of two matrices or the addition of two matrices, where you can completely avoid two matrix computation because they are expensive. If you have the two matrices ready, then you just have create a new symbolic matrix which is holding those two matrices. And the most important type is the block matrix that I quickly want to go into. Which is a metric which is really very commonly used in PyGIMLi. We have a block matrix. But we don't see much from the block matrix. That's why we're gonna show the block matrix. But actually, it's saying there are no matrices in there. So we need to add some matrices. So like one matrix, 2x2 matrix, and then adding this to the matrix A at the position 0, 0. But then I'm also adding the same matrix A1 at another position. Because when you constrain different time frame with the same constraint matrix, you don't have to copy it. Then you see you have the two matrices on top of 0, 0, but also on 2, 2. But you can also an identity matrix of 5, for instance, and then add this at a certain position. And this identity matrix, and then you can add a cosmate matrix, for instance, say type 2, 3, and then you add this also, and then the matrix can be on top of each other and can slice each other. It doesn't matter. It's just a block matrix which is being created from several other matrices. Okay, this is what we want to do with matrices. And now I'm going to start with a quick introduction into regularization. So again, I'm using the import functions. I'm not checking the PyGIMLi version again. If you go to regularization, which is an important thing in inversion, we are minimizing some data objective function, which is the difference between data and the forward response, weighted by the error estimate epsilon. This is our data objective matrix. As this minimization problem is non-unique, we add some regularization parameter to it, and for this we're using some operator WM. And this regularization operator is using some constraint operator, and we will illustrate here some types of constraint operators with some weighting functions. So we see this is a mild left matrix. So we have some operator C that can be weighted by some operator, and we're going to have a look at which kinds of operators exist in PyGIMLi. For exemplifying this, we're using a very simple forward operator that we're going to use later on, which is called prior modeling, which is just a mapping operator. Assume you have a mesh, and you have some measured, and you measured the value somewhere on the range of this mesh. Then this mapping operator just finds out the cells of the individual position. So we iterate through all the positions, find the cell where this position is, and we store the idea, and the response of this forward response is just the model at this very position. And similar is also for the Jacobian matrix, which is a very simple matrix with a one value at the ith value of an nth index. And we're gonna exemplify this by on behalf of the triangular mesh of a simple simple domain. So what we're going to do, we import the mesh tools as empty. Then we're going to create a rectangle. There are many create functions. Create a rectangle starting at 0, -10. So we go into the subsurface and ending at 10 and 0. So we have this rectangle here. Okay. Then we create a mesh of this rectangle. And we see, wow, the mesh is very simple because it's just two triangles in. To do some computations on it, you need some mesh quality for the linear triangulation. But still, this doesn't help here. But what we can do is we restrict the mesh size to a certain level, and then we have a triangulation of the subsurface. Now we define some positions where we measure our fields. So we have a probing. So say we have 3 and -3 as a position in the upper left edge, and then we have a 7 and -7 in the lower right left edge. And we measured some values which are 20 and 15. What we're going to do is we create a forward operator modeling, which is taking two different arguments. The one is the mesh, and the second are the positions. Okay, now we have our forward operator. We found one region, and now we set up an inversion instance of the forward operator, and what we will do is to create an inversion. So for the inversion, we create an inversion instance, which is e.g. inversion, and then what we can do is inst.run, and it will of course explain because there are positional arguments missing, and so what we need is for the values is a data wells, and we need the error wells. Let's say our data have an error of data error of 10%. Then we add an error, and then we're going to need a start model. Let's say, well, we have a start model of 10. This could also be a vector. Okay, yes, of course, what we have to do is we need to specify the forward operator. So we use our forward operator, and in this case, we also want to have some output of the inversion, and then we're going to run the inversion, and it's after 2 iterations, it's fitting the data almost perfectly, which is natural because we have only 2 data. And to show the inversion result, we are returning the result from the inversion, then we show the result. And for now, I'm turning the verbose off so that we see a little bit more. Okay, if you look at the result, we have a value of 20 here and a value of 15 here, and in the middle, and the rest there's some middle. So what we have by default is first order smoothness. What you now can do is to is to set regularization parameters. And for doing so, I will check all those parameters into an inversion keyword args. So that I can, this is producing the same result, but I'm storing all my arguments for the run so that I can easily run the inversion again with the same arguments. We don't have to recreate the inversion. There's a function set regularization, which is having different arguments. There's a region number, which we can omit. In this case, it holds for all the regions in the subsurface. We can specify a starting model, limits for the parameter, transformation function, constraint type, vertical weight, and define several options for this. We run it again, send keywords, and we are gonna show it again. I'm gonna just copy paste. Of course, the result is the same because this is the normal constraint type. If I'm using the constraint type 0, which means I need to use the result. If I'm using a 0 type, which is a pure damping of a model parameter, we see the model is throughout 1 everywhere, which is the logarithm of 1 is 0. So it's driving the model towards a 0 value. Because the starting model is only a starting model, but if you add the reference switch, then this starting model of 10 ohm meters becomes also a reference model. If you change this, the image doesn't change much, but the whole background is now at 10 ohm meters instead of 20 ohm meters. So we see the damping has a really very low local footprint and doesn't help us much in the inversion. We're going to copy this. I'm going to use a second order smoothness. And here, it doesn't make a difference whether we use its reference true or not, because we will have a very smooth transition. We have the 20 ohm meters around here, the 10 ohm meters around here. And then we have a smooth transition from here to here, even with values above 20 and below 15. If you want to have a look at a closer look at the constraints, then we can access this matrix and see it's a sparse map matrix. We can have a look at this matrix. I'm going to use a less marker size. So this is the second order smoothness, constraint, which is kind of a Laplacian operator. If we gonna call it again with a first order smoothness and visualize the constraint again, then this is looking different. So in this case, we have the mesh of almost 800 model boundaries, and we have 500 and we have 850 model boundaries and 540 cells. So this matrix C is asymmetric and has as much rows as there are boundaries between the individual triangles and as much columns as there are cells. Now I want to go to geostatistics inversion, geostatistical regularization. This is taking not only neighbors into account, but it's having a wider correlation by using an operator which is defined by, for instance, an exponential model. And more details you can find on on a tutorial. Okay.
Yeah, so sorry about that.
Okay.
Ah, there we go. Thomas is back. I'm not quite sure what happened there.
Okay. Yeah. So seems like I have been offline. Okay. So we're going to proceed with the geostatistic constraints. And actually, one thing I wanted to show you before is also the effect of a so-called vertical smoothness factor, which is called Z rate, which is defining the purely how much purely vertical boundaries behave in contrast to horizontal boundaries, because very often we have more or less layer subsurfaces, and in this case we have a footprint of a subsurface which is the regularization footprint is rather isotropic around these points. But if I'm reducing this vertical weight, then we can enforce more or less laterally constrained subsurface models, and then we're going to end up in structures that are more horizontally layered. We can also put it the other way around and have a vertical layering. I just wanted to show you because we're going to need it next time. As time is running short, I will not go into too much detail about the geostatistic constraint matrix, because there's a nice tutorial here. I can
Thomas, maybe just try stopping the screen share briefly. I'm not sure if you can hear me. If you stop the screen share and then try again, maybe that will fix it. Not sure what's causing the problem.
Okay, so I guess there's some error with a PyGIMLi org page not responding. Okay. If you hear me, I can proceed.
Yeah, I think what it might be is that you've shared a specific tab rather than the entire window, and when you switch to another tab, maybe it gets confused. I'm not sure if that might be what causes it.
No, I wanted to. I'm sharing the whole screen, but I wanted to show other.
Well, it's back, so
It's back. Okay. Okay. Okay, but what we also can do is to use geostatistic regularization by a different correlation length in the different directions. I'll copy from here. I'm using a correlation length of 5 meters in both directions, which is producing an image which is similar, but I can control much better on how the geostatistical distribution of my parameters is looking like by defining different correlation lengths in the horizontal and vertical directions, for instance, or also using a dipping vector so that my result is dipping in the one or the other direction. This is what we're going to use also in the next tutorial. I'm going to start with the ERT field data inversion with a region-specific behavior, which is the lake case. This measured data have been measured at a lake, across a shallow lake with about 2-3 meters depth. And what I'm doing is I'm loading the data and printing the data. Actually, this shouldn't be. Actually, this shouldn't be blank. But I'm going to step into. I can also show these data. That's not working. But you can see you have a data container with 48 sensors and 658 data points. What I'm doing right now is what I did before. Is I'm plotting the x positions against the z positions, just to see the bathymetry. So we have the first 2 electrodes on the shore, and the last 2 electrodes on the shore, and in the middle we have a bathymetry, which is about 2.5 meters deep. The whole profile is 80 meters long. So that's very nice. I want to show my data. But it doesn't. But does tell me there's no apparent resistivity in the data. Of course, when I'm looking here, there's A, B, and N. Current electrodes, potential electrode. There's some errors in it. There's some current and voltage and resistance in it, but no apparent resistivity and no geometric factor. Apparently, I need the compute the geometric factors of this data. And what I'm doing is to putting it into my data container. And I have also a geometric factor K. Then I need to compute my apparent resistivity. By multiplying the resistance of measurements with a geometric factor, and then I also have apparent resistivity. And now I can use ERT show or PG.show. There are many ways to the target to show my apparent resistivities. I have a pseudo section, which is not a subsurface representation, but what I see here is I have a Wagner beta. I have a Schlumberger measurement with a small dipole in the middle and an enlarging current dipole, and in the second part, on the lower part, I see a Wagner beta measurement. All those data, all those 2 different data types show an increasing resistivity with depth, starting from about 20 meter to about 100 ohm meters at maximum, and I want to do an inversion of this data set. So first I need to compute a mesh. So what I'm doing first is using the mesh tools. I have to import it. Then I'm using the function mt.create paramesh PSC. I'm using a depth of 20 meters, and what I'm doing here is just for visualization purposes. Is very small boundary. Usually the boundary around the inversion mesh is much bigger, but in this case I'm going to use a very small boundary, and the result is called PSC. It's a piecewise linear complex. I'm going to show this. PSC which is indeed strange, because it has always been working. Start over again. Something's going wrong here. I'm gonna start a new. Something's going on here. It has been working right now, and it's not working anymore. Purpose of live coding. Okay, so I'm gonna show this late case in the ready tutorial. This is really really a shame, but it has been working right now, and for some reason something's not working here. Okay, we are at this point. If we show this this parameter mesh, then we have this PLC. Then we see the lake button topography. We have the boundary of the background region around it, and then we have the inversion domain here. But what we need is a water domain. What we and if we plot the nodes and the shore, if we plot the first 12 nodes, then we see the node number 8 and 9 and 10 they're at 0, and then they're going down to the down into the bathymetry. And if we go to the left, so what we do is we connect the node number 10 with node number 100. So we take PLC node 10, PLC node 100, and give it a marker of 1. And then we add a region marker at a shallow depth at around the middle of the profile at 10 centimeters depth, and give it a marker 3. This is our water body. And if you show this, then we have 3 regions: the background, the inversion domain, and then the water body. Actually, what I'm doing here, I'm creating a mesh, so that this whole domain will be subsurface discretized and showing it again. What I'm also doing is I'm getting rid of those marker 1, which is the lake boundary, because this is leading to problems. So what I'm doing is I'm searching through all the mesh boundaries. I'm using a loop for all mesh boundaries. And if this mesh boundary is -1, and if this boundary is not outside, which means above here, if this is inside, I'm setting the marker to 2. And if I show it again, I have my mesh manipulation and see the mesh marker and see the boundary marker of 2 inside of inside of a mesh. Now I can do an inversion with it. So I'm setting up an ERT manager. That's what we did last time. So I'm starting an ERT manager with ERT data. I'm saying verbose is true. I'm setting a mesh, which I have constructed previously by the function setMesh, and then I'm doing an inversion, a standard inversion. And we see the chi-square value is going down to 2, which is not as low as I would expect. But if we look at the data fit, which is the data, the measured data on the left-hand side and the model response on the right-hand side, we see an arm as a 3%. It's pretty good, and we can hardly see any obvious difference between the two. But what we have to do is to look at the misfit function. So that's why we use the function manager.showMisfit. And this is producing the relative misfit of data and model response. And there I see a lot of systematics in the data. So there's still some structure in the data that needs to be inverted. Should actually be a random distribution of Gaussian noise. I'm going to show the results. So I'm using a constant keyword argument, which is defining the minimum color map and maximum color map, a logarithmic color map with this certain color map, and I'm showing the result. And if we see this, then we have a subsurface image which is very smooth, and then we have a very low resistivity, which is actually lower what we expected, because when we measured with a conductivity meter the conductivity of water, and we found out a value of 22.5. So actually here the resistivity is below 20. To access what's happening in the water, I'm using a very interesting function which is called mesh.submesh. So I'm extracting a submesh of a mesh, and I'm using all mesh cells that have a mesh cell marker of equal 3, which is all the water body. Then I'm extracting from the manager model the last water cell count values from the model, and then I show it, and I'm showing only the water resistivity. And I see very low values of 5 ohm meters up to 19 ohm meters. So which is far below the 22 ohm meters. But actually, I know something about the water, so I should try to limit this. I already explained the set weight value, which is the vertical weight, and if I'm using this vertical weight here, then I can see I get a much more layered subsurface, and I also see in the water layer there are some values below 20 ohm meters, but there are much more around the expected values. So even the regularization, the strong regularization disturbed my fitting, because now I see I can reach my chi-square value of 1. And now I see in the subsurface we have a water layer with still too high resistivities here, but we see some layering, which is a muddy sediment layer probably, and some higher resistivity bedrock in the subsurface. This is a much better image. But actually, I don't like what's happening in the water. That's why I'm setting region-specific regularization. So I'm using the same functions. I'm using the inversion object inside of a manager, and use the set regularization with a keyword argument, with a non-keyword argument number 3, which is the region number. And I'm saying, well, my water body should be limited between 20 and 25 ohm meters. There are several functions to limit this. Usually this is done by a logarithmic transformation. And if I'm doing the inversion, I also end up with 1 ohm meter, and I see very nicely my water body is almost constant because I limited the value. I can still fit my data, so this was obviously a good idea, but I see very low resistivities below the water. So maybe something's wrong with my constraints, enforcing some artifacts, or there's something going on the subsurface, maybe a muddy. I could also limit my regularization, limit the resistivity of my subsurface layer, number 2. But this can also plot. This can actually fit my data and produce a model that is above 20 ohms in the whole subdomain. So actually, there's not a big difference between those two models. So if I'm pretty sure that my values are above 20 ohms, I can constrain them to be above this value by this limit function. But actually, I would expect my water body to be a constant body. So what I'm doing is I'm keeping off all limits. That's why I'm setting for all regions a limit of 0, which means no limit at all. And then I'm setting the number 3, the water body, to the so-called single flag, which means all the triangles in this water body are reduced to one unknown in the inversion. So there's only one water resistivity being inverted. Again, I can fit my data. And if I'm plotting the result, I have this value. And if I'm looking at this value, it's at the very end of my profile. It's the very end of my model vector. So if I'm plotting my model vector, I see a value of 21.8 ohms. So actually, this was a nice idea. I kept it free, and the inversion automatically set up an inversion a water resistivity of 21 ohms, which is really nice. But I can also, if I know it exactly, there's no need for any inversion. So what I also can do is use the fix argument, and I'm fixing the water conductivity to 22.5. Again, I'm able to fit the data with a chi-square of 0.5. Very good fit. And in the result, I observe almost the same subsurface structures, but the water body is gone because it's not part of the inversion anymore. While in the single region, it is projected back. The one unknown is projected back into the whole water body. Now the whole water body is outside of a domain. What I can also do is to use geostatistical correlation lengths. In this case, I chose a value of 30 meters in horizontal direction and 2 meters in the vertical direction, and then I'm ending up in a resistivity image, which is also fitting the data, but looks very layered because I really enforce the layering. So this you have to be careful with these region layers. I can also do, just for matters of completeness, I can also couple those two regions that are otherwise decoupled. So there are, as those are different regions, they are usually decoupled, but I can couple them by using the inter-region coupling argument. Then I'm getting a result which is, again, very implausible with high resistivities in the water, but there might be other cases why this behavior might be meaningful. As a takeaway message, you should always have a look at the data fit and get your hands on the data error. And we see a lot of models can fit the data equivalently, particularly in this full space case. So you need to control your regions, and you need to constrain or fix whatever it's possible to fix and reliable, and play around with your parameters. And geostatistical constraints can sometimes outperform the classical smoothness, but sometimes it doesn't. So you need to be careful with this because all you should be encouraged to play with regularization and keep looking at the data fit and play with regularization and compare the different models. Okay, now I'm trying to go back to my third notebook. Maybe this is going to work out. I'm going to do it again in style. So we have learned a lot about regularization schemes and different kinds of regularization, how we can control the subsurface, and this is something we want to use for a specific case. Case is incorporating prior data into inversion. This is assume we drilled a borehole or drilled a direct push sounding and we have a data set which is called bedrock x set r. The x position is constantly 155. The set position is increasing, and then we have the resistivity measured by direct push sounding. So we start looking at that and read in the data by numpy again from txt. X set r, you can call it whatever you want. We unpack all the columns and name the columns x, y. Now x set and resistivity. And then we want to plot them. So I'm going to generate a subplot, and then we plot a semi-logarithmically plot the resistivity over the depth, which is already negative, because in our definition set counts upward, and so minus depths are below the surface. I'm adding a grid layer. So what we have here is a clay layer at the top. Then we have a interbedding of silt and sand layers in the middle. Then we clay again, and we have a resistive bedrock at the bottom. Okay, then we're gonna do an ERT measurement, and we're gonna load our ERT data. We're gonna use the function ERT load that can load a lot of different data formats, and we're gonna show this data. So we have 64 sensors and 1,000 data, and we're gonna show this data. So we, unlike in the last case, we don't have to do anything with the data. The current resistivity is again combined of two different data sets: a Savannah Alpha data set and a Schlumberger data set, and we can also look at the errors, which are already nicely estimated, starting from 3% to 4%. So we can actually go right into inversion with those data. So again, we create a manager, an ERT manager, put in the data, verbose. We're going to use depth of 30 meters. We don't have to create the mesh before. We can also input all mesh arguments also in the invert command, and I'm gonna limit the maximum cell size to 100 square meters here, and then I'm gonna see the inversion parameter depth is a bit too deep, but then we're not gonna see too much in this notebook. Okay, so we see a really straightforward data fit to the of chi-square 1. So we're going to have a look at the result and look at the data fit. And the result are already explaining something. Well, we see a recent undulating bedrock topography is increasing resistivity, but it does not much in common with our sounding that we have measured. But actually, what I'm doing is I'm finding some keyword arguments to make the result nice and reproducible so that we can compare different results. And I'm also returning the axis and the color bar of a show result argument, and then I'm just plotting the positions of the direct push measurement so that we can see where we have our measurements. Decreasing the marker size, then we can see that there's a larger spacing of a point in the upper part, and there's a higher spacing where there's a lot of things happening. Actually, we want to have a comparison between those type of push data and our real data. So what I'm doing now is create a position vector, as we did before in the other term. And I'm iterating for all the sit, x, and z values, which is just a pair. And I'm using this position vector. And I'm using an interpolation function. Xz. Yeah. We can extract our mesh, the resistivity from our mesh at the same position. Okay, now we want to plot it. I'm going to step over this part a little bit. Again, I'm creating a subplot. I'm plotting the Bohr value, and I'm plotting this resistivity measurement, and I'm seeing what the ERT inversion result does not resemble my 4-layer model at all. So what I want to do is to improve my model. So what I'm also tend to do is to set a regularization. And plotting the result again. So just decreasing the vertical weights for the resistivity a little bit. Actually, when I was testing, this was all much faster, but seems like we are approaching a nice result. Yeah, actually, I can also take beforehand that we can similarly good feed the data and have a model which is what we have before, because we have changed our regularization scheme. So we're going to just use the before mentioned figure to plot the second ERT inversion. Yeah, so now we can fit the data. Data is looking a little bit better. It's only gradually showing this. So we can improve this a little bit by using even lower values of set weight, and this can improve the value. But actually, what we want to do is to try geostatistical inversion. So I'm using only the inversion domain, and And I'm guessing at a correlation length of about, well, typically the correlation length in the horizontal direction is very large. In the vertical direction, I would guess from these behavior, we could do a variogram analysis. We could do a variogram analysis at about 5 meter correlation length, which is a bit less than the thickness of these layers. And I would assume a factor of 10 higher correlation in the x direction. So I'm going to do the inversion with a geostatistical inversion. And again, already plotting the values on top of each other. And we will see that the geostatistical inversion is now showing the layered so the low resistivity, high resistivity, low resistivity. But when we do the comparison in detail, we see well, it's nice behavior, but the high resistivity layer is too thick, and the bedrock becomes too deep, which is very common for people doing ERT inversions. Actually, we cannot use the direct push data too much just by optimizing parameters. We are kind of at the end right now. So what we have to do is actually those are data. So why not using those data in the inversion? And that's what we do in a so-called joint inversion framework. There's a ready-made framework, joint modeling, that combines the different forward operators, and that's what we're going to do. So like in the other example, I'm gonna like in the other example, I'm using this framework. Import using the prior modeling and setting up the prior modeling. And I'm calling this forward operator FOPDP, like direct push. What I need to do is I need to extract the parameter mesh from the actual mesh, and that's and for this reason, I again use the function create submesh. So I'm extracting all mesh cells with a cell number of 2, and extract it in the because I want to do the prior inversion only with the inner inversion. So okay, so I'm taking the mesh of a manager that I have been taking before, and what I can do right now is to take a forward response of the last inversion model, which is extracting my resistivity at the positions. So my prior model is extracting the resistivity at a certain positions. I could even set up an inversion with this. Using the direct push operator, forward operator, then the taking this inner parameter mesh as the mesh, and then set regularization. Somehow it's lacking. Then I could do run. I'm giving the measured direct push resistivity also an arrow vector, and I'm using the a 10% vector. When the result is ready, we'll show it. And something's not working right now. I'm going to show you the ready prepared result. So I'm going back to the I skipped the part where we also could use the prior data as structure information and included a structural constraint, but we already did it last time. You can have a look at this in the original tutorial. And if you do the inversion of those data, then you can see the exact transition of the direct push data in the model and the inversion if somehow extrapolating the data to the outside. You can also use geostatistical correlation links, and then you have a different sort of extrapolation function to the outside, which can be better, which can be worse. Actually, what we want to do is do a joint inversion of our ERT data and direct push data. So we import also from the frameworks, we import also the joint modeling. We set up an ERT modeling, set the mesh, set the data, set the joint and set the joint modeling by just combining two different forward operators. So we're going to use the ERT forward operator and the direct push forward operator. We set the mesh for the joint inversion forward operator. Then we set the data, which is also like the forward operators. They are just combination of two forward operators. This is the combination of the ERT data and of the vector of a resistivity. Then we create a model, which is our starting model, and we're gonna do a response, a forward response of our joint forward operator. And if we split this into the ERT forward operator and direct push forward operator, then we can have a look at the ERT forward operator and at the direct push forward operator, which is of course constantly 100. We can create a Jacobian for T Jacobian on top and the direct push Jacobian on the bottom. So we have 1,200 ERT data and about 100 or 50, 60 direct push data that are gonna weight it into inversion. So this is how the direct push metric is looking like. What's important is we go into joint inversion. So what we do is we create our data vector. So we concatenate all our apparent resistivities together with our measured resistivity. We concatenate the same way our data errors with in this case I use 20% data error because I've seen that the data fit is not very good. And I'm going into inversion using the joint forward operator, using logarithm model transform probably. This is always default. Then we run the inversion with a starting model, and then we see that with a normal smoothness constraint, we have a perfect resembling of our direct push data at the points where they are, but they don't reach very far into into the subsurface. That's why we're going to use geostatistic constraints with correlation lengths of 50 and 5 meters as above. And we can nicely fit the data. This means we can fit both ERT and direct push data. And we have a model that is in the middle fitting our depth sounding and also being extrapolated. And we have a kind of an idea how the clay and sand and silt content is looking like outside. So the layers seem to be continuous a little bit. So if we again take our model response and split the model response into two parts, then we can see that the misfit function looks very Gaussian. And if we now look at the difference between the measured borehole data and the direct push data, we see a very nice alignment. It's still not perfect. There's something going on also with a direct push measurement, maybe a scaling factor or whatever. But we can really incorporate this data into the joint inversion. So still, ERT data is highly ambiguous, particularly for hidden layers. And prior data can help to improve regularization. Structured data can be of help, but it doesn't make sense if you only have point information. But point data improve the images, but it can only make real improvements by geostatistical extrapolation. To conclude, to make an overall conclusion, somehow my computer is hanging. If you have a specific problem, you should use specific regularization, and those matrices are the key to the efficient inversion and sophisticated inversion. And you can really use PyGIMLi to solve your own problem, do reproducible research, contribute your ideas and solutions. We would be highly welcome any contribution from any ideas for improvements, any solution, any nice case study, or even do your research and tell us that you did it with PyGIMLi. There are other frameworks to be used. There's petrophysical inversion, there's block joint inversion, there's also lateral or spatially constrained 1D inversion, and there are other things that we are still working in. Actually, those things are ready and become ready classes in PyGIMLi, so we have a full frame constraint inversion, like for a full time-lapse inversion or inversion along the frequency axis. We have in structurally coupled cooperative inversion, cross-gradient frameworks, also for joint inversion of separate data set and including additional equations. And there's a lot of things that need to be done to speed up the whole algebra, to replace the CGLS solver, and then yeah, there's a lot of future work to be done. And I recommend you to go through all the because time was running too short, to go through all the tutorials in your time. Take your time to play around. But I also want you to have a look at other packages in the PyGIMLi environment, which is the BIRD package, but there's electrical resistivity, there's reproducible data analysis, there's Nico Skipper created a package of coupled magnetic resonance and little electrical resistivity, which is doing a lot of electromagnetic stuff, and structurally coupled cooperative inversion framework that is going to be implemented into PyGIMLi. There's also a very recent implementation of an electromagnetic modeling toolbox, which is called Custom by my colleague Raphael Rochlitz, which is modeling and also 2D, 3D inversion of control source EM data by using PyGIMLi, and not only for the mesh generation, but also for the inversion part and semi-upper electromagnetics. And there's some references. And yeah, with this I would close up and want to apologize for the late for the technical problems and for the rush that I made in the last hour. I hope you get an idea on how on what you could do with PyGIMLi for your own research, and you are welcome to have a look at all the examples, documentations, and so on. Thanks for your attention.
All right. Thank you very much, Thomas. I definitely saw quite a lot of interesting stuff there. I don't really work much on PM, but I can see it's got applications elsewhere as well. So thank you very much, Thomas. That was, PyGIMLi, another overview or another tutorial on some of the advanced or some more complicated things compared to last year that you can do here in PyGIMLi. If you found this video useful, please do share it. There's still a bit happening with Transform. As I say, we're just over halfway through, so we've still got one more talk today, and we've got a few more tomorrow. On all sorts of interesting geoscience, digital geoscience things. So thank you very much for all your attention. Thanks again to CurveNote for helping out with the organization of this. Do have a look at the Software Underground. The links are all down below. And with that, thank you very much, and we will see you on another one.